Now, I really want to turn my focus to what's happening down within, how is this information being translated to the bay itself? So the question that we're answering is, what are the trends in nitrogen, phosphorus, and suspended sediment loads being delivered to the bay from the non-tidal portions of the watershed? Now, to answer this question, we turn to the results, or the loads that are derived from the 9 river input monitoring stations. Now, the drainage area that these river input monitoring stations capture is about 78% of the entire Chesapeake Bay drainage area. And you see that based on the white areas below these river input monitoring stations, there is still that 20-some% of the basin that's not captured, and then there's some point sources and all that really contribute to the downstream load. So what we're describing is, what is this portion contributing to the downstream receiving waters of the bay. Oops. So this plot should be familiar to most of you. It's really our total load to the bay plot generated by the Chesapeake Bay program, and it brings in all those different sources of information. The blue bars represent the cumulative load from the 9 river input monitoring stations, and then we have monitored loads from the wastewater treatment plants, the simulated loads from non-point source areas down below the river input monitoring stations, and then atmospheric deposition. So what we know is from the cumulative load from the 9 river input monitoring station, that accounts for about 63% of the total load delivered to the Chesapeake Bay. So the question is, what is the trend within that load being delivered to the bay? So we still turn back to what we're getting out of WRTDS. And what we've done here is we've added up all of the loads from the 9 river input monitoring stations, and they're each represented here by the black dots, and those are equivalent, to the blue bars represented on this plot. And again, we see that there's considerable variability within that load. We see the effects of dry years and wet years within it, and through WRTDS we can integrate out that variability and identify what is the overall pattern in the load being delivered to the bay. One thing that I brought in is the overall contribution to that total load. For total nitrogen, we see that Susquehanna River is contributing about 60% of the load, whereas the Potomac is contributing about 24%. And as you get down into the other basins, there's just minor contribution relative to those two watersheds. What everyone is asking is, what is the trend within the nitrogen being delivered to the bay? So we can roll up the response from the 9 rim stations, and this really is the overall pattern of what we see being delivered to the bay. And you could basically surmise from this that over the long term, that load is improving, and we see that improvement starting to taper off or slow over the most recent 10 years. But the bay really doesn't see the total load being brought in as one slug. It's coming in through different tributaries and into the different estuaries. So what we want to do is break this signal down into its individual patterns. And that's really where we can start to bring in our statistics and saying what's happening at each of the different river input monitoring stations. So this is that signal broken down in each of the individual basins. So we really see the Susquehanna was probably driving that total trend that we were seeing in nitrogen, where we saw early improvement with slowing of that improvement, and within the Potomac we're seeing some improvement as well. What I want to point out is the reason you really only see the Susquehanna and the Potomac and a little bit of the James, we're showing these in load units. So we're seeing most of the materials coming in from the Susquehanna, lesser amount, but still more from the Potomac compared to the other stations, and then the James. So what we want to do now is take that information and take it to a per acre basis, so normalize it based on drainage area, and see what those trend results are. And what I wanted to point out here is, although the Susquehanna and Potomac are the largest contributors of nitrogen in a total load basis, all of the rim stations have an influence on the receiving waters within those respective estuaries. And we'll show you what those patterns are here in just a second. So now what I brought in, and this is pulled from a summary that we have on our webpage, we have the changes in total nitrogen delivered to the bay from the 9 rim stations. So all the 9 rim stations are listed here from largest to smallest, And then I've broken the total nitrogen load trend into two categories. The long-term trend, which is basically 1985 to 2014, and the short term, which is 2005 to 2014. On the long term, we see that the vast majority of the stations, 7 of the 9 stations, are showing improving conditions. The chop tank is the only station showing degradation. If we go to the short term, we're seeing that we're losing some of that improvement. We have 3 of the 9 stations that are showing improvement, whereas 4 of those 9 stations are showing continued degradation. So what I want to do now is take these short-term patterns and put it on to the plot that we have. We've got these normalized loads, these per acre loads. So now what we want to say is how much mass is being reduced at each of these stations. So we have on the x-axis the change in load in pounds per acre, and then we have our 9 river input monitoring stations stacked from the Susquehanna at the top to the chop tank at the bottom. So what you can see from this is we have 3 stations that are showing improvement with a percent change ranging from 10% at the Potomac and Rappahannock to 14% reduction at the Patuxent. Again, this is over the 2005 to 2014 period. And then for the degradation, we're seeing 4 of the stations are showing minor degradation. This is in the 2 to 4% range, with chop tank showing the largest degradation. The Susquehanna is showing no trend, and we really saw that in the previous plot where the Susquehanna's trend is slowing down in the most recent 10 years. So now for the total phosphorus loads delivered to the bay, we have the same setup, and now instead of 63%, the 9 rim stations contribute about 69% of the total load being delivered to the bay. We do have other contributions through point sources and the non-point sources below the fall line or the river input monitoring stations. So what we want to do again is turn to these blue bars, the 9 river input monitoring stations, and say what is the pattern within those loads, which you see here by the black dots, that we see a different distribution of what's contributing to that total load. The Susquehanna is contributing about 45% of the total load. The Potomac is 29%, James 18%, and Rappahannock is 5%. So we're seeing the other basins contributing more of that phosphorus than what we saw for nitrogen. The remaining stations are contributing 1% or less. So for the overall pattern within the phosphorus being delivered to the estuary, we're seeing there's basically a general tendency to increase from 1985 to 2014, and the rate of increase has really stepped up over the most recent 10 to 15 years. So if we break this signal down into its individual stations, we see the following pattern. So again, from top to bottom, these are the flow normalized loads in millions of pounds per year from 1985 to 2014. The orange bar at the top is the Susquehanna and the pattern we see over time there, followed by the Potomac in green, the James in purple, and then the Rappahannock is really the last one you can distinguish in the dotted green. So for the Susquehanna, we see short-term improvement from 1985 to 95, and then since then, we've had degradation. And we know that there's the infilling issue within the Susquehanna, and there's a team of individuals that are really researching why Susquehanna is becoming more sensitive to releasing more phosphorus and ultimately more sediment down to the estuary. For the Susquehanna, we had an early period of improvement followed by degradation during the late 90s, early 2000s, and now we're seeing improvement over the most recent 10 years. And then the James, very similar pattern to, say, the Susquehanna as well. So that's how that total trend is broken into its pieces. So let's look at the trend results. So for the changes in total phosphorus load, again, pulled from our summary on the web page, we have our 9 river input monitoring stations broken into long-term and short-term. We see that we have a mixed bag of trends here, more so than what we saw in nitrogen. For the long-term, we see that 4 of the stations are showing improving conditions and 4 of the stations are showing degradation. As we move into the short-term period, 2005 to 2014, we see only 2 of the stations are showing improvement, 4 are showing degradation. So if we look at what that means on a change per unit area, we brought in, again, the 9 rim stations. We have now anywhere from the range is an increase of 15 pounds per acre to a decrease of 20 pounds per acre on the x-axis. And you really start to see what's happening within each of these tributaries. The Susquehanna shows the greatest degradation at about 0.15 pounds per acre increase over this 10-year period, and that's a 44% increase. Then we see within the James about a 12% increase, and then on the Choptank about a 19% increase. The Potomac really is the only station that's showing market improvements within each of these 9 stations. So the question I have for others, especially those that are focusing on the estuary, how are these trends translating to what we're seeing down within either the living resources or other measures of water quality conditions in the estuary? So basically our summary within the non-tidal network for nitrogen, phosphorus, and sediment, we're seeing more of our stations showing improving conditions than we're seeing in stations that are degrading. Phosphorus has 3 times as many stations that are improving instead of degrading. Nitrogen has twice the number of stations, and then we have about 10 additional stations that are showing improvement at sediment compared to what's degrading. For the loads delivered to the bay, we saw that it really is a mixed bag. We have several stations that are improving and several that are degrading. What I'm interested in is how does that information tie into what we're seeing within the estuary. So what we are doing next, basically we're following the STAR work plan for feeding the midpoint assessment. What I've gone over today is how we're using our monitoring data up in the non-tidal network, translating that into what a measure of progress within improvements in nitrogen, phosphorus, and sediment loads. There's an analogous piece that's going on within the tidal waters, taking the monitoring data and looking what's happening within the trends. We take all that information and we break it into, we're going to be explaining what's happening within those trends, what's changing in the watershed that's driving the trends that we're detecting, and then how can we take all this information and enhance the Chesapeake Bay watershed model, which ultimately then informs the development of the WIPs and assessment of progress. The information that I went over today for both the non-tidal network and what's being delivered to the bay is all provided within our newly released Chesapeake Bay or the non-tidal webpage. And I believe we may be going through a little bit of what we have on this webpage, but everything that I've gone over today can be either downloaded in data sets or maps or talked about within our summary on this webpage. Thank you.